Hey everyone, a very warm welcome back to the channel. And today we have another very interesting question from the house of matrices and determinants. So the question is asking that let A be a matrix such that Aij is equal to 0 if I is equal to j. So the diagonal elements are basically equal to 0 and all other elements which are off diagonal elements are equal to 1. Then we have assumed that B is the inverse of matrix A. First of all, we have to prove the existence of B, and also we have to prove that diagonal elements of the matrix B represented by BKK will be constant. So in short, we can also just say that we have to find the inverse of the matrix A, because once the inverse we have found out, easily everything else we can do. So the maximum time allotted for this question would be 9 minutes, and ideally you should try to do it within 3 minutes, and then you can return back to have a look at the solution. So I hope all of you have tried it out. Now the solution as far as it is concerned, so concepts and formulas used would be matrix multiplication, and that in a matrix is invertible if and only if its determinant is non-zero. Now what we are doing is that we are letting a matrix which is given to be this quantity as p minus I, where p is the matrix whose all elements are 1 1 1 1 1. So basically what we have written it as is all ones, all elements are 1 and minus 1 1 1 0 0 0. So basically identity matrix we are subtracting, that's what we are doing. So that would obviously result in this particular matrix, because 1 minus 1 1 minus 1 along the diagonal will make all the diagonal elements 0, and the remaining elements will still remain 1 1 1 only, because these are 0. So 1 minus 0 is still 1. So that's what we have done. Now what we are saying is that let Q be equal to the square of the matrix P. So it is very obvious to us that by definition of matrix multiplication, Qij would be equal to, because you can write it as P into P, right? So it would become Pik into Pkj, and both of them are actually equal to 1, because all the elements of matrix P are 1. So 1 into 1 is 1, and the summation would come out to be n. So all the elements in the matrix Q are actually equal to n. So Q is nothing but n n n n n n n n n, right? So basically all of them are n n n n. Doesn't matter what is the order, right? It does not need to be 3 by 3, any order, but all elements are n. So obviously you can take out n common and write it as n into 1 1 1 1 1 1 1. So this again becomes P matrix. So what we can say is that Q is equal to NP, right? Now the thing is, from this relation A is equal to P minus I, we can write P would be equal to A plus I. Now we can square both the sides. So on squaring, what are we going to get? We are going to get P square is equal to A plus I whole square, right? So A plus I whole square is as it is, but P square would be equal to Q, and Q is equal to NP, and N into P, and P is A plus I. So that's basically what we have done, just substitutions. Okay, then we have opened this up and we are getting a square plus I plus 2a is equal to na plus ni. Finally rearranging, this is what we get, which we are calling as the equation number 1. Now of course we can take a common from here and then take determinant both the sides. On taking determinant, this would be n minus 1 whole power n, and here it will become determinant a into determinant of a plus 2 minus n into I. So obviously this can't be 0, because this quantity obviously is non-zero. So since the determinant is not equal to 0, we can say A inverse would exist, which we can call as B. And now what we are doing is the equation number 1, we are multiplying both the sides by B. So basically A square I have written as A into A, then we are post multiplying it by B. So B is here plus 2 minus n into A into B. Then again the same thing happens here, I into B becomes simply B. So A into B is I, because it is the inverse of A. So A into I again becomes A. Then the remaining things remain as it is, just that AB again we substitute I, and here it is n minus 1 into B. Rearranging, of course, we can get the value of the A inverse as B is equal to A plus 2 minus n into I upon n minus 1. So basically this is pretty much all that there is to do. But since we are being asked about the diagonal elements, so both the sides of the matrix we can take the diagonal elements. So diagonal element for A matrix would be AKK, For I matrix, we are calling it as IKK, and for B, we are calling it as BKK. So of course, the thing is that AKK is equal to 0, and this actually is equal to 1, because diagonal elements in an identity matrix are always equal to 1. So BKK comes out to be a constant actually from this equation, which is 2 minus n upon n minus 1, which obviously is a constant. So it was not a very difficult question. It was just a little bit tricky, otherwise not very difficult. And I'm pretty sure you all might have found this a little bit on an easier side, just that it was a little tricky. So next time when you encounter such kind of a matrix, you might be able to easily, spot what trick would be used in these kinds of questions. So thank you all for sticking back till the end of the video, and make sure you like the video, hit the bell icon, never miss it to never miss an update. Tell me in the comment section what you like the most. And thank you so much to all of you for the 500 subscribers, and subscribe to the channel, share it, and I'll see you all in the next one.